Just like, just didn't make sense.
I think it's for their own. Because, yeah, here, I'll show you. Yeah, it's 18. Yeah, it's 18. Because. It was 19.
Yeah. I haven't covered that enough. Because on the side it was mostly naming. And I was like, okay, so last one. Yeah. I just know that they. I just can't say it. Yeah. And the thing is, what was that we doing on Thursday? She started with reaction stuff. Oh, wait, we're already doing that, I guess. But this. I just wrote down. I don't know. Yeah. Wow. It was awesome. After, I was super.
Yeah, I didn't.
Yeah.
But I didn't miss.
This was like the whole down.
Yeah.
And I was.
Which I'm hoping.
This was like 2. You know, so that's.
Yeah.
So I tried. Yeah, well, I had so much of that. That I just take out the whole, there's no way. But
Vegetation.
the dough was out.
Yeah.
I had an HVAC show to get.
Oh, great.
Which was one of the first things. But then when she don't have that.
Yeah.
I was just saying, I got that's pretty good.
Yeah.
How did you feel about the tennis? You think it was? Oh, okay.
But they all are having and I already know I'm like so even for the actually yeah. So same like
Oh, yeah. Right.
But I saw. Yeah.
Okay, folks. Just FYI, you will have your exam back on Monday in lab. I'm almost done grading. I just haven't quite done it. So you will get your exam back on Monday. That's one of the things I will always say is you will always get your exam within 1 week of taking the exam. I may be horrible with labs, but I'm not horrible with exams. Those are something I work hard to get done quickly. Second announcement I have is you will have a homework over what we're going over today that will be due on Monday. Third announcement that I have is that the lab that was originally scheduled for Monday is not going to be due on Monday because we haven't gotten to that information. So you don't need to worry about coming to lab with that lab completed or us working on that lab during lab because we've got other things we need to cover. So I will be lecturing during lab. I'll try to do it for probably only like an hour, hour and 15 minutes, and us get out a little early because it's hard for me to lecture for more than that. And I know it's also hard to absorb more information than that. So that just gives you a heads up leading into next week. So again, you will have a homework that's due Monday. You will have no lab due Monday. We will hold off on that lab. And then I will return your exams to you on Monday. Any questions? Okay, so today what we're going to do is we're going to finish up chapter 15 and move on into chapter 16. Chapter 15 has been about aldehydes and ketones. Chapter 16 gets into amines. After the amine chapter, then we start really getting into carboxylic acids and their reactions. And then we can finally start moving into the biological reactions. But we're going to talk about some of those reactions a little bit here and there even today. So the first thing we're going to talk about is hemiacetal, hemiketal formation. After we talk about hemiacetal ketal formation, we're going to talk about how sugars are actually hemiacetals and hemiketals. Once we talk about the behavior of sugars as hemiacetals and hemiketals, then we're going to talk about acetals and ketals and how they are formed. Finally, in this chapter, we'll talk about the hydrolysis of acetals and ketals to reform the aldehydes and the ketones. So basically, the beginning of this section talks about taking the aldehydes and ketones and converting them into acetals and ketals. The last part of this section takes the acetals and ketals and converts them back to the aldehydes and ketones. And then we will get into amines and talk about primary, secondary, tertiary, and quaternary ammonium ions. We'll also talk about how to name amines, which is the first time we've really encountered something that's quite a bit different than the typical naming system. And it's not drastic, it's just a little different. Any questions over the plan for today? Okay, so hemiacetal, hemiketal formation are addition reactions. Basically, you're adding something to the carbonyl carbon bond. In the case of hemiacetal hemiketal formation, that something that you are adding is going to be an alcohol. Now, we're not good about showing lone pairs when we write out structural formulas. But if you go back to Lewis dot structures, you would understand that there are lone pairs on our oxygens in both the aldehyde ketone as well as in the alcohols. So again, if we go back to Lewis dot structures, we would find out that there are lone pairs on these oxygens. Now, what happens is that the lone pair on the alcohol attacks the carbonyl carbon. Now, because carbon can only have 4 bonds, that forces the double bond in the carbonyl to be kicked up onto the oxygen. And you temporarily create a negatively charged species, which rapidly goes out and grabs the hydrogen. So what is formed when we have this reaction is we will take our aldehyde in this particular case, and we will form an alcohol along with an ether. Where our carbonyl was. So again, the lone pair on the alcohol initiates everything. The lone pair on the alcohol initiates everything. It attacks this nice trigonal planar, which is a completely flat structure at that carbonyl carbon. Because carbon can only have 4 bonds, when that OH or that alcohol oxygen attacks, it causes one of the bonds in the double bond of the carbonyl to be kicked up onto the oxygen. Since double bonds are created of negatively charged species, when that double bond gets kicked up, it forms a temporary negative on that oxygen that was the carbonyl oxygen. That negative charge then goes out and grabs the hydrogen from the original alcohol. And what you're left with is an alcohol on the original carbonyl carbon and an ether on the original carbonyl carbon. Now, hemiacetals and ketals are actually pretty unstable. So as quickly as that alcohol ether structure is formed, it will go backwards to reform the alcohol aldehyde. The same thing goes with our ketone. Again, the lone pair on the alcohol attacks the carbonyl carbon. Because carbon can only have 4 bonds, it kicks the lone pair up onto the oxygen. In kicking that lone pair up onto the oxygen, it temporarily forms a negatively charged oxygen. That negatively charged oxygen then goes out and it grabs the hydrogen from the original structure. So again, with our with our ketone, we form an alcohol and we form an OCH2CH3 group in this particular case, where an ether group. Again, this hemiketal is extremely unstable, so it's going to go back to the ketone alcohol, our starting material. Questions about the general process for a hemiacetal or hemiketal formation? Now, as I said, hemiacetals and hemiketals are pretty unstable. They tend to revert back to their alcohol and aldehyde or ketone. An exception to that, though, is sugars. Sugars would prefer the hemiacetal or hemiketal structure over the straight chain. Again, sugars prefer the hemiacetal, hemiketal structure over the straight chain. So here is the straight chain of glucose. Now, most likely, this is not the form of glucose that you typically see in your textbooks on nutrition. Again, that is because the straight chain in the aldehyde formation is less stable than the hemiacetal is. So what happens is that the lone pair on the next to last oxygen, on the next to last carbon, the lone pair on the next to last carbon attacks the carbonyl carbon within itself. Just as before, this causes the lone pair on the double bond. This causes the double bond to break. And the electrons in the double bond are temporarily placed on the oxygen. That causes the oxygen to go out and grab the hydrogen from the original alcohol. Just to help us keep track of everything, I am going to highlight the elements that are part of the reaction. So this goes to form a ring structure of this nature. Now, your original aldehyde is this grouping right here. That's your original aldehyde. Your original alcohol is there. Folks, it's the exact same process. I'm trying to let you get it written down so that we can then just look. It's the exact same process. The alcohol lone pair attached the carbonyl oxygen, kicking the electrons in the double bond up onto the oxygen of the aldehyde, making it temporarily a negatively charged species. The electrons in that negatively charged species then come and grab the hydrogen. The difference is we have created this hemiacetal all within one structure. And so it winds up forming a cyclic structure where the oxygen from the alcohol attacked the carbonyl carbon, kicking the double bond up onto the oxygen, which then went out and grabbed the hydrogen from the alcohol. We will actually talk about hemiacetal acetal formation and being able to predict where these alcohols are in greater detail, because typically the way it is written is a little bit different. A lot of times the way you're going to see this written is you're going to see it written in this format. So in other words, we just get rid of all the hydrogens. And we don't draw out all the carbons. Any questions about how to make a hemiacetal or a hemiketal? Yes.
How do you know which oxygen? There's a lot.
Okay, so what you're going to find out is that the oxygen that is doing the attacking is always going to be the one on the next to last carbon when we're talking about sugars. Always going to be the one on the next to last carbon when you're talking about the sugars. Is that what you were?
Yes.
Okay. So basically, folks, the key to a hemiacetal hemiketal is on the original carbonyl carbon. When the reaction is complete, you're going to have an alcohol and an ether. Again, the key to a hemiacetal hemiketal is on the original carbonyl carbon. You will have an alcohol and an ether when the reaction is complete. Now you may ask, well, how do you know if it's an acetal or if basically what it came from? How do you know if it came from an acetal or whether it came from a ketal? The answer is in what's attached to the carbon that has the ether and the alcohol. If it's a hydrogen attached to the ether and the alcohol, then it came from an aldehyde. But up above, when I did both, come on, stop being pickle. Again, if it came from an aldehyde, you will have a hydrogen attached to the carbon that has the alcohol and the ether. But if it's a ketone, you will have a carbon attached to the carbon that has the alcohol or the ether and the ether. That means that it had to have come from a ketone. So it's that other element that's attached. Is it a hydrogen attached or is there a carbon attached? Two carbons attached. Okay, so the difference between a hemiacetal and an acetal. A hemiacetal only has one alcohol attacking. An acetal has two alcohols attacking. So let's look at the acetal formation. Again, you're going to have a lone pair off of an alcohol. That alcohol is going to attach to the carbon. The carbon is then going to kick up its lone pair of electrons. That lone pair of electrons is then going to go out and grab the hydrogen from the alcohol. So that as an intermediate, you make the hemiacetal. Now, the difference between the hemiacetal and the acetal is that you are going to have an additional alcohol. So you have two alcohols that react. And in the acetal, again, you're going to have another lone pair that is going to come up and it is going to attack. It is going to kick off the alcohol entirely. And that alcohol is again going to come out and it's going to grab the leftover hydrogen. So the process is the same, but what results is an acetal, which has two ether groups attached to what was the original carbonyl carbon. So the hemiacetal that we've been talking about is actually the intermediate to acetal formation. One alcohol comes in, attacks the carbonyl carbon, kicking the double bond or breaking the double bond. And then that lone pair goes out and grabs the hydrogen, and you make the hemiacetal. The difference between the hemiacetal and the acetal is that you have a second alcohol, and that second alcohol goes and attacks that carbon, the original carbonyl carbon. In this case, it kicks the hydroxide completely off, which goes out and grabs the hydrogen. So you have the acetal as the final product. And you have water. Now, you will note that in both these cases, there is something on the arrow. Hemiacetal and acetal, or that, excuse me, acetal formation requires an acid catalyst. Acetal formation requires an acid catalyst. It also requires careful formation because we're about to talk about the reverse of an acetal. And folks, what I'm describing for an acetal would work for a ketal also. What I just described for an acetal works for a ketal. The last thing that we're going to talk about, so we've talked about hemiacetal, hemiketal formation, where you added only one alcohol. We talked about acetal ketal formation, where you added two alcohols. Now what we're going to talk about is the hydrolysis of an acetal ketal, which basically, folks, is the reverse process. That's what you can think of it as, is the reverse process. When we make an acetal or a ketal, we have to be cautious to remove excess water as water is formed. When we make an acetal or ketal, we have to be cautious to remove the water as it is formed. Because the destruction of an acetal ketal back to the aldehyde or ketone simply requires water and an acid catalyst. So if you leave that water there, in the formation of that acetal, since it's already in the presence of an acid catalyst, if you leave that water, it's going to cause the reaction to go in reverse. So we actually have to be conscientious. If we really want to form an acetal or a ketal, we have to be conscientious to remove the water as it is formed. Otherwise, we will get the reverse reaction where in the presence of water, which, by the way, can be rewritten as HOH. In the presence of water, the lone pair on the water can attack that carbonyl carbon, kicking off that OR group, which the oxygen of can come in and grab the original water, the original hydrogen. So what we wind up doing, if we're not cautious, if we leave that water present, what we wind up doing is we wind up taking our acetal or ketal, and we wind up converting it right back to a hemiacetal or a hemiketal. And then if there's still water present, we can repeat, the process repeats. Oops, that's supposed to be an R. The process repeats itself, where again, the OR is kicked off, the lone pair is brought in, and what we wind up forming is our original carbonyl. Plus another alcohol. So again, let me go back into this thing. I'm trying to let you draw it and then me go back through it again. So if you're not careful and you have water present, the water, oxygen can attack the carbonyl, what was the carbonyl carbon. If it attacks the carbonyl carbon, what it does is it breaks this carbon-oxygen bond, kicking off that OR group. That OR group goes out and grabs the hydrogen from the original water, and it makes an alcohol. It also forms the hemiacetal or hemiketal. Now, as long as there's acid catalyst present, we can continue this process where the OR group is kicked off to make another alcohol, and the original alcohol goes back to form the carbonyl carbon. Double bond oxygen. Hydrolysis is simply the reverse of acetal formation or ketal formation. Hydrolysis is simply the reverse of the acetal formation or ketal formation. questions about hemiacetal formation, hemiketal formation? Again, hemiacetals and hemiketals, they're not particularly stable unless it's something like sugars. And sugars love to be in the hemiacetal, hemiketal formation. Questions about acetal formation or ketal formation? Basically, that's just where you have two alcohols reacting with your original aldehyde or ketone to make two ether groups. And then finally, the hydrolysis of the acetal or ketal, which is essentially the reverse process of the acetal ketal formation. Okay, we're going to look at some examples because that's a lot of information. Okay, so are the following compounds a hemiacetal, a hemiketal, or neither? The first compound we're going to talk about is this compound. What I see when I look at this compound is I see an alcohol, I see an ether, and I see a hydrogen. It is because of those three things that this had to be a hemiacetal. Let's look at another compound. I see an alcohol. Actually, I see two alcohols. And that's all I see. So this one is neither. Let's look at another one. Because this one is actually tricky. I do see an alcohol. And I do see two ethers. One here and one here. But the alcohol ether nor the ether are on the same carbon. So this is neither. Let's look at one more. Soon I'm going to give you a couple to figure out. I just wanted to walk you through some examples. First thing I note is I do see alcohols. I see two of them actually. And I do see an ether. And you will notice that it's on the same carbon. So it's a hemiacetal. Does that help you figure out how to look at it to determine if it's a hemiketal, or hemiacetal? If it's a hemiketal, you would have two ethers, but they have to be on the same carbon. If it's a hemiacetal, you've got an hydroxide or an alcohol and an ether on the same carbon. On the exact same card coming off the second. So you'll have an OCO group. If it were a hemiacetal. I mean, a hemiketal. Okay, let's look at another question. Okay, so what are we looking for on this? Let's talk about it. Acetal. What am I looking for? Two ethers. On same carbon. With a hydrogen. Whereas if it's a ketal, I'm looking for two ethers on same carbon attached to two other carbons. And I guess over here with the acetal, you could say and carbon. Let's look at this. So we're going to start with this one. I want you to figure out what that is. And then I'll show you how to determine what it came from. So what did you decide it was? Okay, yes, this one is ketal. We know that it is a ketal because we have two ether groups. There's number one. And here's number two. And it's attached to two carbons. So it is a ketal. Now, For the other half of the question, it says draw the original aldehyde or ketone. To do so, folks, the easiest way is to go, okay, let's break off the ethers. So if I break off the ethers, what I have left is this structure. And what did we make? It's either an aldehyde or a ketone. Since this was a ketal, it had to come from a ketone. So that would be the original structure it came from. Let's look at another example. This one's more challenging to think about. Because you really have to think about what's missing. What's missing is how many bonds does carbon have? So what's not being shown right now is that there is a hydrogen here. So what we have is we have two ethers. Attached to a carbon and a hydrogen. So what is it from? Or what is it? This one is an acetal. Now to get back to the original, again, we're going to break these bonds. And when you break those bonds, you have CH3, CH. With that being your double bond to oxygen. The other, if you want to know what the other material was, it was a diol. 2CH2, CH2, OH. That would have been the other reactant. Questions? Let's look at another problem. So in this one, you're going to draw the structures of the hemiacetal, hemiketal, formed in the reaction. First one we're going to do is going to be this structure. And the second one, while you're at it, is going to be for this reaction. What I note when I see something like this is I see the word Hemi. Hemi. Hemi tells me that it's going to be one OH and one ether. So on this first one, the OCH2CH3 comes into the double bond, to make your ether, and then it becomes an OH. In the second one, that would be the product, because again, the alcohol comes into the double bond to make a ether, and then that double bond becomes an OH. Questions? So we've actually already done that, but I want to do one of these. What aldehyde or ketone will result from the hydrolysis of and it has to occur in an acidic environment, in water that's acidic with an acid catalyst. So a lot of times they'll show it as a hydronium because that's both water and the acid catalyst. The main reason I wanted to do this one is to take something that is written in all in one line and help you to differentiate what it actually means. So you do have your benzene ring attached to a CH2. Then you have your carbon. Now, the next piece where it's got the OCH3 in parentheses, 2 of them, it means that attached to that carbon, there are 2 of those groups. And then the rest of that is attached to the carbon as well. So that is actually what we're working with on this hydrolysis. So once you write it out in that format, it's much easier to see because again, hydrolysis means that you're breaking the bond between the ethers. And where those ethers were attached, that is what is where the carbonyl group will be attached. So the answer to that question, again, I took and I broke off the OCH3s and replaced it with the carbonyl group. And so this is the actual starting, this would be the ketone that ketal could be made from. Questions about, I know I've spent a lot of time on hemiacetals, acetals, ketals, hemiketals, hydrolysis of ketals, hydrolysis of acetals. Any questions? We're not going to name acetals and ketals. But I spent the time because we are going to come back to the formation of hemiacetals and hemiketals in particular when we talk about carbohydrates and sugars. And so I wanted to spend enough time that you're more comfortable with this topic so that when we come to it and we're forming the sugar chain, the sugars, you at least know the reaction already. And it's just a matter of helping you figure out how to determine what hydroxides up and what hydroxides down, and then how to connect them. Yes.
So questions similar to these be like on tests or homework?
This will be a lot like, so on a test or a homework, I don't know the homework because I haven't looked at it in active. On a test, you can guarantee where I would have given you something like this piece right up here and asked you for the product.
Okay.
Just like I did the other reactions. Or I could give you the starting ketone, and whether I give you 1 or 2 alcohols would determine whether or not you make the hemiacetal or if you make the ketal. Because the difference between hemiacetal and ketal is hemiacetal requires 1 alcohol. Hemiketal requires 1 alcohol. That's it. Acetal ketal requires 2 alcohols, and an acid catalyst. And then the hydrolysis requires that you start with either an acetal or a ketal. And you do you go in reverse where you have an acid catalyst and water. So those are the three possibilities really for this. Now, will you potentially have to make acyclic sugar? Yes. Because we're gonna get into those. I just don't know when that will be, but in general, it'll come in the reaction section.
Would that be similar to like we had the straight chain glucose and then
Yes.
transform it into the
Yes.
cyclic? Okay.
It'll be just like that type of thing. And until we get to the carbohydrates chapter where we talk about taking the straight chain and knowing which direction the hydroxides are going to be and stuff, I won't expect you to be able to determine that until that point. But once we get to that part, that chapter, I'll expect that. I don't have time to get into amines. So, Monday morning, we will definitely be going through 16.1, 16.2, 16.3, sixteen point four, no, 16.5, 16.5, and maybe 16.6, which is the entire chapter. 16 is pretty short. Any questions? Okay. I will see you Monday morning.